Okay. You ready? Okay, yesterday we talked about laser and electron beam, and we talked about their numerous differences in the manners in which laser and electron beams interact with materials. And for those of you that weren't here, you can watch the movie. But we went through 7 different types of things. But the first one was electrons. Electron beams use electrons. Lasers use photons. There's a factor of roughly 500,000 difference in the energy between an electron and a photon. And that means that electrons have a lot more momentum and power to penetrate and do other things than photons, which just heat on the surface, things like that. So it turns out electrons being charged particles, and this is getting to number 8, the beam will be distorted by magnetic fields, and lasers is unaffected by any fields except gravitational fields on an astrophysical basis, okay? Yes, light will bend when it goes around the moon, okay? Not usually a problem in welding.
What's the difference between an electron beam and an arc full of electrons?
Okay, the electron beam is generally generated in a vacuum at very high voltages on the order of 40,000 to 100,000 volts or more, okay? So the electrons have 40,000 electron volts, whereas in an arc they got 4 or 5 volts. So the electron energy, if you will, is 1,000 times higher, or 10,000 times higher in an electron beam than it is in an arc. The electrons are carrying the current in an arc, but as we're going to see in a second, we might be talking 100 or 200 amps in an arc at 20 volts, whereas an electron beam you're talking 40,000 or 100,000 volts at up to a half an amp. Okay, so the voltage current ratio is quite different. Okay, and so those electrons have a lot more power than they do. I mean, in an arc, they're punching through the boundary layer. In the electron beam, they have to punch through several thousands of metal. Okay, which is, if you think about it, remember that boundary layer is a rarefied gas, and so you're probably talking about the metal having 2,000 times the density of the boundary layer. And so, well, I can penetrate part metal because I have such high energy beams. Now, yesterday someone asked about welding in space, and I said, well, we kind of had a discussion. You can, those of you that weren't here can watch the movie, but I talked about potentially in space what you ought to be using is 10,000 volt electron beams, which is sort of a hybrid between arcs and electron beams. Okay, so you can have an electron beam. I mean, your question is an excellent one in the sense there's a continuous spectrum of electron energies from arcs to electron beams, but in fact, to get that extra 2 orders of magnitude, we go to very high energy electrons, okay? And in fact, you go to higher energy electrons. I might as well pass this around. We've talked about the vaporization pressure. This actually was given to me by the folks at White Oak, the Naval Surface Weapons Center. And these are the guys that had spent $250 million of Star Wars money trying to develop these relativistic particle beams that they're going to shoot down incoming missiles, and I mentioned that yesterday. This is a number of layers of Kevlar, which I'm sure were held in a solid steel clamp, and they hit it with a 1.4 million electron volt, 3/4 million amp, 100 nanosecond pulse, okay, which is 35,000 joules per pulse. Now 35,000 joules is a lot of energy, and you can see how the thing is, the Kevlar is cupped, ablated slightly on the surface, all with 100 nanoseconds of 1 pulse, okay? And all it takes is a $50 million machine to do that, okay? And as I told people yesterday, they shut the program down because instead of being able to shoot the beam 30 miles into the air, they were able to shoot it to 30 inches into the air. So that, they figured that probably wasn't going to protect you against the exocet, okay? At least the exocet probably had an explosion diameter of more than 30 inches, so anyway. If you might knock out the exocet, but you'd also, it's still going to do its job. Okay, the electron beam produces X-rays. Those X-rays mentioned yesterday, if you're at 100 keV, you have to have some lead shielding. If you're at 1.4 MeV, you have to have like 3 inches or 36 inches of concrete, okay, to shield from millions of electron volts. The laser, the problem with lasers, if you ever worked with some, most of you probably have worked around lasers or whatever, is you have to wear goggles that will not transmit the infrared, because the laser infrared is invisible, And if it hits your eyes, it can blind you very quickly, particularly the power levels you're going to be using for welding. So in fact, you have to, if you go to a laser welding setup in industry, it'll basically, the whole thing's enclosed with lockouts so that if no one can walk into the robotic cell and get hit with the laser beam and all kinds of shielding. And that just ups the cost of the capital equipment. Okay, that's how you get to $1 million for the capital equipment. It's all the shielding and everything else around there, either for X-rays or for the infrared reflections. The electron beam, the current is actually limited. If you want to weld and have sharp focus, the current is limited to about a ½ amp max. In fact, most machines don't go above about 0.2 of an amp. And the reason is, once you get to about a ½ amp, the electrons are so close together, even though they're going through there almost the speed of light. These are relativistic electrons, okay? They're close to the speed of light, more than 99% of the speed of light at those voltages. They are so close, there's so many of them. Remember this, in a coulomb, there's 10 to the 18th electrons or whatever, 10 to the 19th or something. They're so close together at a ½ amp that they actually start repelling each other, okay? So if I want to get a good sharp focus in my beam, I can't have the electrons in my beam repelling each other and spreading the beam. So I have to stay at relatively low currents if I want to get a good focus for welding. Now if I'm trying to melt something, they have electron beam melting units. Most of the titanium the Air Force uses is made in these huge electron beam vacuum melters, and the beam might be 4 inches in diameter. You don't care, you're just trying to heat the metal. You're not trying to weld and penetrate and get high power density on the surface. So those machines can run at 3, 4, 5 amps, okay, for melting of titanium. But if I'm trying to weld, I'm limited to a few tenths of an amp. And if I'm limited to a few tenths of an amp, let's say I'm at a 40 keV beam, and that's the one that I don't have to use lead shielding for my X-rays, and I'm at 0.2 of an amp, that's only 4 kilowatts. Well, 4 kilowatts really is not going to weld anything more than about 3/8 of an inch or so. So if I want to weld thicker things, I actually have to go to the higher voltage machine where I have to pay for lead shielding and I have to worry about, you know, everybody wearing X-ray badges all the time. Or I have to, well, that's actually all I can do. I mean, if I need that extra power to get to 20 kilowatts or whatever. If I want to get to very heavy section, and people have welded, well, the British, just to say they could do it, welded aluminum. And aluminum is easier to deep penetrate weld because it has lower density, and so the vapor cavity, you can drill deeper in a less dense material than a heavy material like steel in terms of the sidewalls collapsing on you. In they welded 20-inch thick aluminum in the laboratory just to be able to say they could do it. Okay? Actually, they didn't weld it. They melted through a solid block. Okay? Because if they had tried doing that with 2 blocks with an interface in between, the odds are their alignment would have been off by, you know, 20 milliseconds of angle or something, and they would have missed the beam, missed the joint, because it doesn't take much. But they did. You can penetrate 20 inches in aluminum. It's been demonstrated in the laboratory. It's not practical. In fact, an electron beam, about the, and this might actually be the next point, about the greatest depth to width ratio you want is about 10 to 1. And the reason is, if you come in and make something that's very thin like this, not only will you miss the joint if you're off by some angle or if you're off by some translation, but you also, if that thing has any tendency to form a shape like this, you're going to end up with a solidification defect right in the big areas, because the stuff shrinks from the sides in the bigger area. All the shrinkage is going to be trapped right in there. Common problem. You need walls that have a slight taper to them so that it solidifies like that, and walls that are straight. So it turns out the focus of that electron beam and the optics, the F number if you're a camera bug, but there's an F number to the optics of the electron beam, just like there is for a camera. That F number has to be a big F number so that you have nice parallel sized beams. You don't want the thing coming in and the beam coming in like this, and crossing over several times because you get more energy in certain locations, okay? You don't get parallel sides. You want the beam coming in like that, okay? So you get nice parallel side view. Select taper parallel side beams. In,
Is there a depth to width ratio for lasers that you want to go above?
actually, lasers is kind of the same thing, although the problem is with lasers, when you're doing it in air, and with types of power densities, because lasers are less efficient, we're kind of jumping ahead a little bit. Lasers are less efficient, usually don't laser weld above a ½ inch anyway. And so you typically don't even get to 10 to 1 on lasers. You might get to 5 to 1 or something. But yeah, they would have the same problem if you had a high enough power laser. Lasers actually have a problem of diffraction spots, and I passed this around once before, first day of class or whatever. This is a piece of polymethyl methacrylate plastic, and typically they use this and they just shoot the laser beam and they pulse the laser beam on it and it'll blade off some of the plastic. And what I want you to look at, this was a 5 kilowatt laser. This was the diameter, about 1 inch, of the lasing cavity. Okay, to get higher powers, you have to have a bigger laser tube, and then you focus that down for welding. Well, if you look on this, it's got bumps. It's cold. Okay, it's got bumps on the skin, and that's because of diffraction spots. When the light is coming in, you'll have plus and minus reflections in the wavelength of the laser. In fact, there's something called TEM mode, which means transverse electromagnetic mode, if I remember. But if you want to look at a beam where you have a half wave in the X direction and a half wave in the Y direction, you get basically kind of a Gaussian shaped beam. This is looking straight down on it, but you'll get a Gaussian shaped beam. If I have a beam where I have a full wave rather than a half wave, and then the other one is a half wave, I will have plus, minus, plus, minus, right? Yeah, okay. I'll end up with two regions where I have the light reinforcing the other wavelength. Maybe this one should be another full wave. Anyway, and I'll have two regions where they're essentially canceling each other. And so I'll get those create diffraction spots. What you want is the Gaussian mode, but to get the Gaussian mode, that lasing tube has to be laminar flow, no turbulence in the gas that's doing the lasing and stuff. And so it means you run at a much lower efficiency and a lower power for the same size laser. If you want really high power lasers, you get this multi-mode that you see on that thing with the bumps.
You mentioned earlier that lasers can do about a ½ inch or so. Can you do multi-pass welds with lasers with electron beams like you can?
Yeah, but you're going to have filler metal. Okay, so yeah, you can do the same thing we do in arc welding of heavy sections and lay down a little strip and then another one and then another one. And in fact, they're starting to do that. They have experimented with lasers on panel lines in shipyards, for example, where you're welding, 1 inch thick material or 1.5 inch thick material, but they're adding metal and they're doing multi-pass. So you can do multi-pass. Laser is just another heat source in that sense. Okay. People have tried out a vacuum electron beam and things, but we talked yesterday about all the problems with that. It turns out the electron beam is nice because it's easy to manipulate the beam with magnets. In fact, there is a big application for electron beams in heat treating or surfacing of steels and other things, because all you have to do, you can move that beam around at 10 kilohertz. And you can raster it just like a TV scan, or you can do Lissajous patterns. The problem with a TV scan, you always get bumps on the ends. Okay, you travel over, and as you stop to go back the other way, you have to stop and then reaccelerate, and so you get more energy on the ends. Anybody know what a Lissajous pattern is? No electrical engineers in here? A Lissajous pattern is basically, if I put in 2 sine waves on an oscilloscope, I set up the oscilloscope not for X and T, voltage and time, but I set it up for voltage in the X direction and voltage, another signal in the Y direction, and I end up with sine waves crossing each other, okay, one in X and one in Y. The beam will actually follow these kind of patterns. It's not exactly like a conductor waving its hands, but it will follow these patterns, and the patterns don't have any acceleration. The thing's running at constant speed. Okay, so as it comes in tangentially to the edge and moves out and stuff, you can actually design your Lissajous, or you can design your system with Lissajous patterns so that you get uniform heat across the surface and you don't get any edge effects. Okay, so but that's easy to do. You just have different frequencies on your magnetic fields that are oscillating with speed. So they can do some pretty fancy things. With lasers, it's all done with mirrors and fiber optics. We talked yesterday a little bit about the mirrors. Fiber optics we didn't talk too much about. What happened was about 15 or 20, well certainly 20 years ago, the largest fiber optic laser that you could get might be 100 watts or something. It wasn't very high, and the reason was the fiber optics were not that transmissive. They weren't that clear. They didn't have enough purity to let enough of the light through. If you got 100 watts and you're dissipating 2 watts in the fiber optic starts heating up, and glass doesn't conduct heat very well, and so you end up, blasting your fiber optic. But San Diego National Lab had a project because they had something to do with welding of nuclear material, and they ended up with a project to develop high-quality fiber optics. You could go to 1,000 watts or 2,000 watts. I think they finally achieved 2,000 watts. So now you can use YAG lasers, yttrium aluminum garnet, which is actually near the visible, with 2,000 watts. And so now you don't have to, you now can have the light going through a fiber optic, and you don't have the problems of stray radiation, big enclosures, for up to about 2,000 watts, which lets you do a lot of things. Anybody use what's the Gillette razor that has, is it 3 blades? Mach 3. 5. Is it 5? They got one with 5 now. But if you look at that, it's got little spots on it. That's laser welded, okay, with a pulse laser. So, in fact, they offered me the machine about 10 years ago that they developed that on because it was their development machine, not their production machine. Laser welded. Again, high volume, okay? Lasers are good for high volume. Okay. In electron beam, because of these very energetic electrons, when they interact with the material, they basically heat up everything in the material. It turns out the laser, on the other hand, we mentioned yesterday that lasers will preferentially couple into ceramic non-conductive materials, and they will be reflected to a certain extent from metals that have free electrons. And so it turns out lasers, they found, actually couple into inclusions in steels better. The Naval Research Laboratory was kind of the center for, in the 1970s. They had one of the first 25 kilowatt lasers. It's about the size of this room, okay? But for research, they were welding 1/2 inch and 3/4 inch thick steel, and they actually found on HY80, they actually got better properties in the weld metal for an autogenous weld, because when they went in there, they found that they had preferentially vaporized away the inclusions. Okay, it was a way, we actually use electron beams in melting to vaporize out a lot of the inclusions, and we call it, well, we used to call it, well, in arc, if you use arcs, it's vacuum arc remelting. If you use slags, it's electroslag remelting. But with electron beams, it's, I can't remember the name of the process, but for electron beams, it's hearth melting. You basically pass the titanium or the steel over a water-cooled copper hearth, and you heat it up to very high temperatures, and you vaporize out a lot of the inclusions. Well, you can do that with lasers and welds, basically is what the Navy found. The lasers would preferentially clean up the weld metal, and they actually got better properties in the weld metal. It wasn't a big enough improvement when anyone uses it, but nonetheless, they did it. Questions on lasers or electron beams? Let me just say a couple of things about lasers and electron beams in terms of, one of the things that I did that when I was over in Japan for a year, so I was a covert spy, an overt spy, okay? The Office of Naval Research was formed in 1946, after World War II, to help, bring over some foreign technology back to the United States, just like the United States brought back all these scientists from Germany and stuff. The Office of Naval Research originally had an office in London, but about mid-1970s they started an office in Tokyo too. And that was because Japan was kind of coming up in the world of science and engineering. The London office covered what was going on in Europe from 1945 till today, and the Tokyo office covered what was happening in the Far East. And so I was asked if I wanted to go to one of these by the guys in Washington, giving me some research money, and they said you can go to London or Tokyo. And I was coming up for a sabbatical. And I went home and asked my wife and said, well, would you rather go to London or Tokyo? And she says, well, I guess Tokyo. And I said, I was a little surprised. And actually, for me professionally, Tokyo would have been better because London's just a bunch of people on vacation. But Tokyo, there was a lot of exciting stuff going on scientifically. And I said, why? And she said, well, if we're going to pick up the whole family and move them, we might as well go somewhere different. Not that England's not different. But it turns out both cities are fairly expensive. But in any case, so I went to Tokyo, and one of the things that people wanted to know about, we just finished the second oil crisis, and the Japanese had a $200 million program to weld heavy section pressure vessels for coal gasification. And these were going to be 30-foot diameter, 8-inch thick steel vessels, very high pressure vessels for the coal gasification process. And this is what people were going to do to solve part of the oil problem. And the only way they could figure out welding these, you can't weld these in the shop and move them because it's like, you know, moving a submarine, 30-foot diameter, but 8 inches thick. This was, you know, heavier than a submarine, but about the same size, okay? And so you had to build these in the field, and the Japanese had this huge program with 200 keV electron beams to weld 6 to 10 inch thick material. And Hitachi and IHI, Mitsubishi, Nippon Steel, all these companies were part of this national program for heavy section electron beam. Actually, it was up to 8 to 12 inches thick. But there's problems. And they did weld some things. They actually had some 2-inch stainless steel vessels for some scientific research thing, and they had to build like 50 of them. And they actually did build a vacuum chamber for this electron beam. And they welded them that way. And they actually also, when I was at, I think, Mitsubishi Heavy Industries, they were welding the Shinkai, anyways, deep diving. It's the world's deepest diving, or one of the deepest diving commercial submarine or research vessel. But the problem is, if you're going to make that circumferential weld on a vessel, you have, and you're going around 30 feet, which is about 100 foot of circumference, you have a problem with long-term beam stability. It takes about an hour or two to go around that 100 feet, even with the high speed of electron beam, because you're going through something 8 or 10 inches thick. And it turns out every now and then you'll get a burst of gas that goes up into the chamber and causes an arc in the electron beam, and you lose your beam for about 0.2 of a second. Now 0.2 of a second is long enough for that weld pool to collapse and lose your penetration. So now, rather than having a nice little keyhole that you're moving along, taking around your joint, you have a defect that's buried 6 inches deep in your steel. And that creates a little bit of a problem for how do you repair that? You dig the whole thing out, fill it up with arc weld metal, and end up with a tremendous residual stress problem. Okay? So that was one of the problems. Lack of long-term beam stability, inadequate repair method for defects, non-uniform penetration. You saw spiking when you saw the video, okay? High equipment costs. These were about $500,000 machines back then. That's just the beam machine without all the other paraphernalia. They would have been $5 or $10 million units. Low utilization factor. I mean, if you use these things, you'd use them about 1% of the time, and the rest of the time you're doing all the other stuff. It turns out you need extremely clean steel and a very low carbon equivalent. The sulfur, phosphorus, and oxygen were lower than, I mean, the steel companies in Japan could make them at the time, but it was kind of a special deal, and they couldn't get it every time. And the other thing is seam cracking is critical, the same problem I talked about. If you're off by a little bit of an angle or something, you miss the whole joint and you end up with a big defect. So it turns out they ended up never using it, but they spent I estimate at least a couple $100 million. Just like our particle beam weapons, they spent a couple $100 million developing something that never worked. But the other part of that story is we were supposed to be overt, and it was good. I was from a university, so the Japanese thought of me as from MIT, and MIT has a big name in Japan. And my boss in the office, though, he liked to sit in the office. He never went out to visit companies, but he liked to visit, kind of mingle and do the administrative things in the office. And so in Tokyo, there was a meeting at Yokota Air Force Base once a month where the various intelligence services, the FBI, the CIA, Naval Investigative Service, Air Force Office of Scientific or Air Force Office, what they call it, whatever they had. But all these covert guys would get together. And in the year I was there, twice he couldn't make the meeting, so he asked me to go out there. And it was very interesting. I learned a lot by listening to these guys. Big conference room, about 20 guys around this table. And then there were about 10 of us sitting in the chairs behind the table, right? Because not enough to sit at the table, and we were just kind of observers in all this. But we had some information, and they might want it. So one of these meetings, there had been a conference down in Osaka on electronic materials or something. This was just a regular old public conference, some society. And a guy from, I don't remember, I think it was the CIA, came up to me and he says, do you have any information on this conference? Any of your people attend this conference? I said, I don't know. I'll ask Dr. Park, who was in our office, who was from the Air Force Wright Labs, and he was over there. He actually been a Korean. He was Korean, and he actually was fluent in Japanese because he learned it in Korea when he was growing up when the Japanese occupied Korea in World War II and stuff. So I go back, and also another guy from the Air Force Investigative Service or whatever came up to me, says, gave me an envelope. He says, here's an envelope, and this guy was there when the other guy from the CIA asked me if someone had gone. I said, I don't know, I'll check with him. And this other guy says, will you give Dr. Park this envelope? I said, sure. So the next morning, I go into the office, and there's Dr. Park, and I sit down with him and said, did you go to this conference down in Osaka? He said, oh yeah, I did. And I said, the guy from the CIA wants a copy of the proceedings. Okay, this is public proceedings, just want to get a copy. And he says, okay. But I gave one to the Air Force. In fact, he opens up the envelope, and there's the money from the Air Force to pay for the copy of the proceedings that he had supplied to the Air Force. So the Air Force guy obviously knew the CIA guy was looking for it. He had already purchased it through Dr. Park, but he didn't bother to tell him because they're in competition. They're not cooperating with each other. Okay, they're in competition. So there was another thing. I had to go to Singapore on something. Anyway, there was some piece of thing, and for whatever reason, I was supposed to go to Singapore and meet with a guy from the CIA, not the CIA, FBI, CIA, anyway, some investigative service. But and whatever it was that I looked at, the report was in the Tokyo office of one of the competing agencies. I met with, so I don't remember who it was. The CIA sent me down there. Well, no, I never worked for the CIA. Whoever, maybe it's the Navy, sent me down there. And it was the FBI or the CIA, but I met with one of their guys who basically took me out to this place and introduced me, and I looked at whatever the technology was. And I told him what I thought and stuff. Before my flight landed in Tokyo, of course, that other agency had the report, right? Kind of did an in-run around the one that sent me down there to talk to these people about it. Anyway, so I learned all about the competition among the intelligence services. And I thought, this is my tax dollars are paying for this redundant information. But anyway, I guess it's good to have competition. But then another guy came up to me once and he says, I understand you've been studying high energy electron beam. And I said, yeah, and I've been doing this overtly for 6 months. And I said, yeah, I've written an article about it because I published my work in the Navy had a scientific journal that was freely available to 2,000 people around the world. And I published 13 articles that year, and I'd written one at that time, hadn't been published yet, on heavy section electron beam, evaluating all this stuff. And he says, well, we have a requirement to learn about what the Japanese are doing. I said, I said, well, I'll give you a copy, a preprint of my article, if you promise not to use my name. Oh yeah, I'll do that. That's exactly what he wanted. Of course, I knew it was exactly what he wanted, because he was going to submit it as he had done all this work, right, for 6 months. So I gave it to him. Hey, he was happy. I knew that it was no competition, because it was never going to get out into the public through them. Right? So, and I later published it, you know, as far as that goes. But anyway, it's a weird outfit. Of course, I don't know if I should tell this one. Okay, other topics. I still shake my head when I think about those intelligence guys. Of course, they always say that that's an oxymoron, right? Okay, distortion. One of the problems, one of the advantages of electron beam is you have low distortion, but that's not one of the advantages of arc welding in general. And in general, there's not a lot of stuff written on distortion. And there actually was a book by Professor Masaguchi, who was in 13A, the Naval Architecture program here for 25 years. He wrote a book on welding residual stresses and distortion. And he was kind of the world's expert in the area of welding residual stresses and distortion. But in general, it's sort of too complex a problem for most people to deal with. So there are some practical things. This is actually a pamphlet put out by the National Shipbuilding Research Program, which is funded by the Department of Transportation, Department of the Navy, and cooperation with Puget Sound Naval Shipyard and Eagle Shipbuilding. This was a program back in the early 90s when they were trying to come up with a bunch of books to tell you practically how to do it. So if I got an 8-inch diameter pipe, or whatever, I don't know if it says what diameter it is, but I got some big heavy valve down here, valve body, and I got some pipe coming off of it, and I get it over to where it's supposed to go and it doesn't fit, I got a problem. I can't just kind of sit on it and bring it back into alignment. I can't really put chain falls on it, bring it back into alignment, or I'm going to break whatever else the chain fall is acting in. Some people are laughing because obviously this is happening in their experience, right? So, so in any case, what you can do is you actually can heat up the pipe at certain locations and bring it back into its proper orientation. And typically what you do is you kind of heat up a V-shaped region with a torch. If you get it up to around the 800 or 900 degree Fahrenheit range, or ideally even up to 1,000 or 1,100 degrees, which is sort of starting to get cherry red, the material will yield locally. It'll actually be in compression when it's hot, and as it cools down, it will go into tension. In fact, a general rule, which I've never seen violated in my experience, is whatever stresses the part has when it's hot, it will have the opposite stresses when it cools. Because when you heat it, if it goes into tension, locally, when it cools back down, it will be smaller. Or it'll be larger, and which means it has to fit in the same space when it's larger, and it's now in compression. Okay, so a good general rule, because people will sit there thinking, well, if I heat it up and it does this and kneels, and they get all confused. But the simple thing is, if you can just say, well, what stress will be on this if I heat it up? Take it from cold to hot. Well, heating up something like this, it's going to be in compression because the local area expands as it heats. Which means in compression, when it cools down, it will be in tension. It's just the opposite. Okay, that's the rule. I've never seen it violated. And I've been going through this for 25 years doing this. Okay? That's not to say I won't find some time when it's violated. Okay, but I haven't found it yet. Anyway, so if you know which direction you want it to move, you actually make it move even further away when you heat it. And people say, oh, you're heating in the wrong spot while you're heating it. And then when you let it cool down, it actually comes back in the direction you want. So one of the problems, you have to have room for it to go even further in the direction you don't want it to go when you heat it to bring it back, okay? Which sometimes is a problem.
I'm just wondering about that because there were a lot of times when pipes on boats didn't match up when you...
Yeah.
How do you know how much damage or...
Oh, what are you doing to the pipe?
Yeah.
Good question. We'll talk about that.
In this
I got a
specific-
story on that.
In this specific case up here, to make that fit,
Yep.
would you just wanna do it on the elbows, those two?
No, you can do it
Or
anywhere you
all
want
four.
along this. I don't,
I'm just trying to think, the one on the upper left and the one on the bottom right would not make it fit, correct?
well, they're gonna wanna bring this one this direction.
Yeah.
And actually, I haven't stopped to think about it, but yeah, this one looks to me like it's actually gonna go the wrong direction.
And
Yeah,
those-
that one,
those
this
two are
one's gonna
do it
be
right.
okay, but this one
That one-
should bring it in, and that one should bring it in.
But that
These
one-
two are gonna screw it up.
Okay, that's.
But it will keep it parallel, if you think about it.
Yeah, it'll bring it back
Cocks-
into alignment
It
again.
cocks the middle part down, but it keeps the flange parallel.
But the guys who are writing this were not rocket scientists. These are practical guys, and so they didn't stop to think, is your drawing self-consistent? Okay? You have to also remember, this is only showing one plane. The thing might be out of alignment this way, and they may have actually, these things may have actually been rotated 90 degrees, and they're just rotating it to a two-dimensional image.
Got it.
So they may have been, these others might have been pulling it back into the plane in and out of the board, and they just simplified it without thinking, you know, when they drew it, okay? Now, one way to think about it, they do try to explain some of these things, but, well, okay, there are different heating patterns that, well, maybe this one's gonna show better, this page. You can go crisscrossing this way or straight down. It's sort of a black art and a bunch of old wives' tales, and one guy likes to do one way and another guy likes to do another way. This is a book by John Stewart, who I'd never heard of before, but a guy who had a lot of practical experience, and he wrote a little booklet. And what does he show? Well, it shows you some of the types of distortion you get. Okay, like this. I was looking for something else he had here. Well, anyway, I won't worry about his right now. So I'll tell some stories instead. So distortion is a significant problem. However, the metal is shrinking, and it's due to local shrinkage of the metal. Okay? If you put the whole thing in a furnace and it heats up uniformly, it all expands uniformly and it cools down uniformly, and there's no distortion. It's because you're heating it locally with a flame or an arc weld or whatever, that the material is locally changing shape and constrained by cold material around it, which causes it to deform, that causes it, when it cools back down, to change its shape and distort. If it's thin, okay? If it's very thin material, you get tremendous distortion, and people try to predict the waves of distortion. If it's very thick, it's surrounded by something that's, 4 inches of steel. Well, that's not moving. The metal, in fact, at that point will shrink in a constrained way, which means you end up with residual stresses. So it's a trade-off between distortion and residual stresses. I mean, the metal you can't fight the thermal strains. The metal is going to move, and if you won't let it move, rather than distortion, it's going to give you residual stresses. Okay, and residual stresses can cause fatigue, cause problems with brittle fracture. So there's lots of problems. Now, what are the kind of rules of thumb for when do you get distortion, when do you get residual stresses? You get absolutely the most distortion when you're less than about a centimeter or 3/8 of an inch thick. Okay, because if you're talking about a typical size piece of steel, and I'm talking steel now, but aluminum's even worse. But for steel, it's about the kind of transition region is around a centimeter. Something that's a big flat sheet, 4 feet long, 10 feet long, 12 feet long, if it's 1/8 of an inch thick, it has no compliance. It has lots of compliance. It doesn't have a whole lot of stiffness. Okay, I can bend it with my hands, right? And therefore, if I introduce some shrinkage stresses, it's just going to create distortion in that thing, and I'll end up with something that's wavy rather than something that's flat. If something is, actually the boiler and pressure vessel code says anything above 1.25 inches thick must be stress relieved before you put it in service if you're building a pressure vessel and it's more than 1.25 inches thick. And that's because the residual stresses at 1.25 inches, by experience, are so severe in most structures, there's so much stiffness in that heavy wall steel, there's no way the material is going to bend or flex or distort to relieve the stresses, so you're going to end up with locked-in stresses, and they will tend to be yield level residual stresses in the material. So you can have 80 KSI, 100 KSI, locked-in residual stresses if you end up with material like 1.25 inches thick. It turns out the material that's right in the middle is about 1 centimeter or 3/8 of an inch thick, and I'll use surface ship guys. What's the thickness of your steel plating on the outside hull? Well, it just happens to be in the worst thickness region you can imagine. You can't predict whether you're going to get distortion or whether you're going to get residual stresses. It really has to do. It's kind of like the old heat flow problem. You're right in the, the Fourier number of 1. Okay, the distortion number, if there were such a thing, of 1. Okay, it's hard to predict. And so actually what the Japanese did in shipbuilding when I was there in the mid-'80s, they had to do a lot of things with distortion controls for reasons I won't go into. They were using a different type of steel that had been quenched and tempered in a different way. And they had potentially huge distortion problems, and they actually would go out and actually build test structures, or they would measure things as they're welding the heavier plate, and they actually measure the amount of distortion, and they would change their process as they're building up the thickness of that plate to correct things as they go. Okay, I'll give you an example. One of my students, my first student ever, John Galati, has been working for Electric Boat as a welding engineer for the last 25 years or so. And he developed a process for the torpedo tubes. They used to arc weld these things together, and I don't know how long these things are. I don't know, but I get the impression they're like 60 feet long or something. But they have to have a very tight tolerance. Well, they would weld these things, get the distortion, they'd weld them heavier section than they need to be, because they'd then go in there with a boring mill and bore them out. It was very expensive to bore out something that long. So John found out that when you're making the circumferential weld and putting these two pipes together, he would actually measure the distortion as the pipe is rotating around on the machine. He would actually have a little dial gauge there. He would measure how much it's getting out of round. And then he would stop, and before he put in the next pass, he had a little program or whatever that would tell the welder where to start the next pass, so he would bring it back into the right angular adjustment, okay? And if he couldn't bring it back to within a certain level, he would have the guy would tell him, grind on this side and put in another weld. So grind out one of the welds you did and bring it back by putting in a second, a weld that you didn't need. And he got to the point where he could, I don't remember if he told me, but he could basically weld those things so they were within a few thousandths, or a few 10,000ths over 60 feet, straight axial, which cut down on the boring costs dramatically. Okay, so that's sort of what the state of the art is to kind of incrementally measure while you're welding and the thing is distorting on you, measure for each pass and make corrections on the fly. That's the best technology. Many, many people over the years, as computers have gotten stronger and stronger and more powerful over the years, people have said to the research agency, oh, give us some money and we will model this in the computer. So in the 1980s, computers weren't very big, so people always did a two-dimensional model of distortion during arc welding. And if you start out with something that was flat, after you arc weld and you get a weld that's kind of shaped like this, it's going to pull up like that. And every one of those models is absolute garbage, okay? Because it's a three-dimensional problem. You can't do a two-dimensional model on what is inherently a three-dimensional process. This thing is heating right here. It's not hot back here, or you haven't even welded it. It's not even connected. You're either going in one direction or the other, and it's either not connected. You can't do a two-dimensional process, a model of something that is inherently a three-dimensional problem. So by the 1990s, we got to the point where computers are powerful enough we could do a three-dimensional problem. The problem is, this is a coupled thermomechanical problem. And all these differential equations you're learning, you can write down the differential equations. We could write down the differential equation in the 1960s or the 1970s. We just couldn't solve them. And you still can't solve them. You don't have the thermal properties of the materials at high temperature. And it turns out, since it's a transient coupled thermomechanical problem, the computers are still not powerful enough and probably won't be for another 50 years if they keep on going at the rate of improvement that they're going. Right now, to solve the real problem would probably take 100 years on a current computer. Okay? It's a huge problem, if you had all the data. So people still get funding to study, do computer studies of welding, distortion, and it's basically money down the drain. The best thing is to do what we call adaptive control. Measure the distortion as it's occurring, and then correct for it as you go on the fly. And it's not just welding, it's the whole forming of curved plates and everything else. And they do laser line heating and things like that on these things to give curvature to plates and stuff. So it's a big problem, distortion and control. Any questions? So I'll tell you that when they made the Shinkai 6500. So this is a study from 2004 on future needs in deep submergent science. So this is a study that the National Science Foundation conducted because the Alvin submarine is sort of getting a little age on it. It was built in the 60s, it got a new hull in the 70s, and sure it's a titanium hull, but it won't do all the things that the scientists would like to do. The Navy actually owns it, but it's on loan to the National Science Foundation. Okay, the Navy. This is a list of, in 2004, the major existing deep diving human operated vehicles. Shinkai 6500, Japan Marine Science Technology Center. Mir 1 and 2 is Soviets. It's a steel hull. Shinkai, I think, is a steel hull, and I believe it was electron beam welded. Based on this technology they developed in this heavy section welding problem. Naval is a French deep diving submersible, which apparently has more time in port than, a lot more time in port than out in the ocean. The Alvin was 4,500 meters. Now, many of you may know that the Navy had the Seacliff. Okay, the Seacliff was about 6,000 meters, and the Seacliff was being used for classified work. The Seacliff is, I think, in mothballs down in Norfolk now, somewhere. It's a little bit larger titanium sphere than the Alvin, and in fact, part of this study they were thinking, well, we could use the Seacliff sphere if the Navy will give it to us, because the sphere is the big cost in one of these things, the pressure hull, and it's like 40% of the overall cost. It's just to make that sphere. The problem with that, though, is the Seacliff being larger and deeper diving and heavier wall would require a new parent ship, because the crane capacity on the parent ship for the Alvin, I can't remember the name of the parent ship, was not big enough for the Seacliff, and so that was sort of a non-starter. I mean, the National Science Foundation had $25 million in 2007 money, I think, to build this, and one of the reasons for the study is could they afford to build one, okay, for $25 million, and could they build one? Not only could they afford to, but did we have the industrial capacity still? Because a lot of the technology and the equipment for the Alvin was stuff that had been torn up and scrapped. It was industrial equipment that the United States, because we've lost a lot of our heavy industrial base to Japan or France or wherever, we no longer had. Companies had gone out of business that had some of the equipment that had built the Alvin. So it wasn't clear if we could build it in this country. And even if it wasn't even clear if we could build it anywhere else in the world other than maybe Japan. So anyway, they did a big study, and I think I mentioned this once before. Here's the table. It's Appendix D. It's the last 2 pages in the whole report. But it, it turns out Woods Hole Oceanographic, which runs the Alvin, and was asking to get this $25 million of funding for the new Alvin. And the new Alvin was going to have lots of other improvements, but they did a study and they said that the whole, if you add up all these other things, it's actually a 2-page table. It was $6,500,000 just to build the hardware. Without, it says on here, extrapolate. Wait, let's see. 6.5 estimated cost, which Woods Hole did, is for hardware only and does not include design, assembly, certification, and testing. And they estimated you double that price if you add all those other things. If you just build the vessel and you don't certify it or design it or test it. And it turns out the Navy has a tank down at Carter Rock somewhere where you can put this whole 7-foot diameter sphere in and pressurize it to incredible depths. Okay, so you can certify the vessel. You do a proof load test on the vessel, okay, by externally pressurize it in a high pressure water chamber. But that costs a little bit of money, okay, to do that. And so this is only half the cost. They were estimating $13 million. I said, oh, no problem. NSF, you got $25 million. Except in 2003, they had actually built the Jason. And anybody know what the Jason is? Jason 2? Jason 2 is a remotely operated vehicle rather than a human operated vehicle. And the Jason weighed, let's see, I think it's on the bottom. The Jason weighed 7,200 pounds. The new Alvin would weigh 33,000 pounds. And the limit on the crane capacity was 40,000 pounds on the vessel that would lower this into the water. But the Sea Cliff, if you went with that, was going to weigh like 45,000 pounds minimum. So we'd have to build a new ship. Okay, so we decided $100 million for a new ship wouldn't fit in a $25 million budget. Anyway, so just the year before, they had actually built the Jason, 7,200 pounds, not human rated. Okay, it's got a cable and stuff, and that works out to $300 a pound as built for the hardware. And this estimate by Woods Hole was 34,000 pounds for $6,500 or $200 a pound. Now, how many of you think you can build something even larger that is human rated rather than non-human rated and do it for 1/3 as much per pound? Well, you can't. And so I had to come up with an estimate of all this stuff. Well, what do I know about frame, fairing, hulls, and estimating these costs? But I had real data from the Jason. This was just guessing data by Woods Hole. And it's typical, give me the money and I will build it. And then I'll tell you about the cost overruns, right? And so all I did is I said 33,000 pounds times $350, not $300 a pound for the Jason. This is human rated. It's bigger, more complex in terms of equipment to build it. I think it'll cost $350 a pound. You say it's going to weigh 34,000 pounds. I multiplied it out, and I came up with like $16 million, okay, as opposed to $6.5 million. Now, then when they went out for bids, I've heard that it actually is costing $18 million. So I think my number was better than theirs. It wasn't off by a factor of 2.5 anyway. But it was still within the $25 million. So NSF could do it, so we didn't tell them they couldn't do it. What? Question?
Well, I was just going to ask, those were all estimates for just the building, once again, not for the certification and everything else? Or did the numbers for Jason include?
No, the Jason was actually saying that we were comparing apples and apples. It was actually, if you get down to it, what's the cost of the syntactic foam? Okay, if you went through each one of those little line items, it was just for the hardware. The Jason didn't include the certification and testing either.
Okay.
Okay, so we were comparing apples and apples.
Right.
But for example, 10% on either one of those, 10% of the cost of the vehicle is the syntactic foam. Everybody know what syntactic foam is? Incompressible foams, okay? It's a polyurethane foam. It's got all kinds of other biocides so the bugs don't eat it. But it's basically got little glass spheres in it that can support tremendous pressure. The polyurethane is packed around the glass spheres. You want as many glass spheres as possible. Syntactic foam was around 40 pounds per cubic foot. Now seawater is 64 or something like that, right? So syntactic foam is what allows it to pop to the surface rather than sink to the bottom if you lose all power. Okay? It's your buoyancy in all your void spaces. So they're going to take this piece of syntactic foam, which I think was costing something like $20,000 a cubic foot or something, for this really deep stuff, because the really deep stuff you had to have glass spheres of different particle size distribution so that you could get a density of 40 pounds per cubic foot. Now, they were projecting that they were going to be able to get 6,500 meter syntactic foam, which is not a big market for 6,500 meter syntactic foam. Okay, it's one of the reasons it's a little pricey. It's sort of a custom job. They were projecting that they were going to be able to get down to 32 pounds per cubic feet, half the density of seawater. In which case, you would even, you improve your design capability even more. But the little spheres, you actually have to, it's designed such that you have big spheres that pack close together, and then you have little spheres that pack in between those. And then, smaller ones that pack in there. So this thing gets to be pretty complex in terms of that. And then you have to have the right polyurethane that'll won't get eaten up by the bugs and everything else. So syntactic foam was a big cost driver. One of the advantages is the offshore oil industry uses syntactic foam now, and so we now have someone else other than the submarine business that uses syntactic foam. And so that has brought the cost down quite a bit, but it's still pretty pricey stuff. Okay, well, enjoy the rest of the videos. If you have some questions, let me know. If you need a special class.
So they'll use it for their motors?